Hello, welcome back to another LeetCode problem. Today we're doing question 33, search and rotated sorted array, medium rated problem. It says there's an integer array nums sorted in ascending order with distinct values. Prior to being passed to your function, nums is possibly rotated at an unknown pivot index. And so we'll skip that part and we'll just, given the array nums after the possible rotation in integer target, return the index of target if it is in nums or -1 if it is not in nums. You must write an algorithm in O to the log n. Runtime complexity. Now, this is very similar to another question that I did a video on. That one was returning the minimum of a rotated sorted array. Let's quickly recap what a rotated sorted array means. Well, obviously a sorted array is of some array which contains elements which are integers, and the property left is greater than or equal to right is always true. Well, we're also told that these are unique elements, so we never have an equal to case. Now let's say that yes, this is the array. How do we rotate it? Well, if we were to rotate it by one indice, look like this, and this 6 becomes the first element. Rotated by 2, rotated by 3, and so on. Okay, so this is what rotating an array means. Now in the previous question that I did on this, we were tasked with finding the minimum value. In this case, we're trying to find the indice of any target. For example, if we're given 5, well, we would have to find it here, and we would have to return 1. Okay, so this is simple enough, but to make it a bit more challenging, we are given a time restriction of O to the log of n. And this usually means binary search. Okay, now let's set up an example that they give us. 4, 5, 6, 7, 0, 1, 2. 4, 5, 6, 7, 0, 1, and 2. And along with that, of course, we are given a target 0. Now, how does binary search work? Well, the first steps are always to assign pointers. We have a left, a right pointer, and a mid pointer. The first step is m equal to target? Well, if so, then return that indice of target, return target. Otherwise, we move on to the next step. And the next step is always to shrink our array that we are searching in to either look like this or to look like this. Notice we're moving the left and right indices because after we would have to recalculate the mid, and it's like doing the question all over again but with a smaller array to search in. Okay, so after seeing that target and the middle element are not the same, we have to determine, do we want to search to the left or to the right? And how do we determine that? Well, in this question, based on this, our first case that we checked was if these two are equal. Now we have two other cases. We have is m greater than t, and is m less than t. Okay, let's look at if m is greater than t at first. Okay, if that is the case, which it is true in this case as well, by the way, well, how do we decide if it's in the left or the right subarray? Well, if we look, the first thing that we could do is we will check if it is in the left subarray, and if it's not, then we know it will be in the right. That might sound a little bit weird, but let's just go through this first. Okay, the only way that it can be in the left subarray is if target is greater than left. Now, why is that? Well, we know that m is greater than target, and by saying that target is greater than left, well, this just means that the left side is actually a sorted subarray, and since target is greater than left, we can say that it's within the subarray. Now, why is it greater than then why is it a sorted subarray? Well, in this subarray, M is actually our new right. And remember, I told you that this equality holds. Well, here, M is equal to R, which is greater than L. So L is less than R, meaning that this subarray is in fact sorted. And that means that, well, since target is actually greater than left, and we know that target is less than M, it's somewhere in that subarray. Okay, now that's one case. Now uh, there is another case where this could be in the left subarray, but it might not necessarily be a sorted array. Now, what do I mean by that? Well, let's say, well, we said here that the middle is greater than the target. Let's create another array where that is true. The middle is greater than the target, but the target is not greater than the left. Well, how do we do that? Let's put a very high number here, and let's increment 5. So this is our left pointer, this is our right pointer, and this is our mid. Okay, now from here, let's search for 0. Well, we can see that target is in fact greater or less than mid. Okay, so it follows that. Now, the other check that we just did was, is target greater than left? And we check 0 is not greater than left. No. But as we can see, 0 is in the left partition. Now, what happened here? Well, the only way that's not possible is if actually this wasn't an ordered subarray. And how do we check that? Well, remember we said that if left is less than right, then it is an ordered subarray. Well, the only other cases where this wouldn't be a ordered subarray is if left is greater than right, where of course right is equal to mid. So if left is greater than mid, then we know that this isn't ordered, and the fact that this isn't true doesn't really matter. Now, why does this being a non-ordered subarray matter? Why would it be in the left? Well, we already said that target is less than mid, correct? Okay, well, if left is greater than mid, that means that the cutoff for the rotated array is somewhere here, which makes the target somewhere to the right of that cutoff, which is true, as you can see. Okay, now if we were to search for any other number, this would fail. If we were to search for 3, well, is target less than mid? Yes, so automatically this would fail, and we would move on to the other statement, which would check if it's in the right partition first. And let's go over that. So for 3, this case, target is actually greater than mid. Okay, now there are again 2 cases where the target could be in the right partition of the array, and in all other cases it will be in the left. Now, what do I mean by that? Well, if we see, it's going to be very similar. Our first check is going to be if target is less than or equal to mid, where of course mid in this case is equal to our new right, or that's not correct. Okay, we're checking if target is less than or equal to right, where right is right. Okay, well, why is that important? Remember we said t is greater than m, and now we're saying that r is greater than t, and in this case m is equal to left, so we're saying that r is greater than left. And this means that the subarray to the right is ordered, and if target is greater than the middle, then it has to be within that subarray. Okay, so that's one case. What's the other case where this could be true? The other case is actually if mid is greater than right. Well, remember, it's the same thing. Mid is equal to left. and if left is greater than right, then we know that this is not a sorted subarray. And let's make an example where that is true. So we want target to be greater than mid, but so the main thing that we want is mid has to be greater than right. So let's start off with big numbers 5, 6, 7, 8, and then go down to smaller ones. And let's search for 1. Now we already said, well, here what would be the mid? The mid would actually be 8. Let's do this instead. 0, 0, 1, 2, 3. And this would be the mid. Well, target is greater than mid. Okay. But is mid greater than right? No. We want a case where mid is greater than right. Let's search for something like 3. Let's make this an 8. Okay. No, this needs to be a small number still. 0, 1, 2, 3. Mid has to be greater than right. Oh, well, this can extend to 8, 9, and then it can go to 2, 3. And let's search for 9. Okay, now target is greater than mid, and mid is greater than right. Well, again, this means that this subarray is not ordered, and as we can see, 9, 2, 3 is not ordered. But the only other meaning is that the cutoff to the rotated subarray is actually here, because if this wasn't rotated, then these would be on the right side. And that means that our target has to be somewhere within it, which in this case would be this one. It is a little bit confusing, and I hope that when you see the code, it does make a little bit more sense. But essentially, we are just checking if the subarray to the left or to the right is in a sorted order. And if it is, then we can easily check if the target is in that subarray, just like we would in regular binary search. We check if it's greater than or less than the mid, obviously. But we also have to check we have to make an extra check in an OR statement, because there is another case where the target could be in it, and that's if the subarray is not sorted. Now, let's head over to LeetCode and see if this can all make sense. Okay, now that we are here in LeetCode, the first step to any binary search is always to set our pointers. And obviously left is the beginning, and right is the very last element, which is the length of nums minus 1. Now, we will continue to search as long as left is less than or equal to right, because if they have crossed each other, then that means that the element might not exist within the array. Now let's calculate where mid is, which of course is the average, but we'll use floor division to divide them. And from there, our very first check, what if we already are at the number? What if nums at mid is actually equal to target? And if that's the case, then we can just return that indice of mid. Okay, now let's break it up into our two cases. What if nums at mid is actually greater than the target? Well, if that's the case, our first check will be, is the left subarray ordered? Or I keep saying ordered, I mean to say sorted. And how would that be true? Well, if mid is greater than target, well, is target greater than the left? Because if that's the case, then it is sorted, because the only way that's true is if left is also smaller than mid, which obviously if mid is greater than target and target is greater than left, then left has to be less than mid. Now we do also want to include an equal to case, just in case target is actually the very far left. Now the other case is what if they aren't sorted? If nums at left is actually greater than nums at mid. Now If that's the case, if either of these two are the case, then we want to search within our left subarray. Otherwise, we're in the right subarray. Okay, now we did the case where mid is greater than target. What about our else case? What if mid is actually less than the target? Well, again, we want to check if target is less than or equal to nums at r, because if the mid is less than the target and target is less than the right, that makes mid less than the right. In that case, it is in sorted order, so it would be in the right side. Or if it's not sorted, in that case, it would also be on the right side, but that's because the cutoff to the rotated array is there. And since we know that the target is greater than the mid, then it's going to be to the left of the cutoff, where the max is, where the higher numbers of the rotated array are. Now here, we go L is equal to mid plus 1, else R is equal to mid minus 1. Now, at this case, in this case, we would have found our index, or our left and right have crossed each other. Now we want to do one final check to see if before we cross each other, the new mid is actually equal to the target, and that is the case for some test cases. In that case, we want to return mid. Otherwise, we want to return -1, because the only way we reach this is if the element does not exist in the rotated array. Okay, well, that should be everything. Just to give everything a quick double check for any spelling mistakes. I don't think I see any, so let's check if this works. There you go. It does very well. And again, this is a time complexity of O to the log of n, because we are using binary search. Thank you guys for watching, and I'll see you in another video.